That's great. Oh, stop. Okay. So I'm going to be talking about I'm Pandatrax. For those that didn't come into the hardware hacking. Oh, it's going in still. It's clip. Go ahead. Okay, yeah. So I can't walk around. It's probably better that way. So I'm Pandatrax. Oh yeah, I know. And I'm going to be talking about return-oriented programming this morning, and which is a great topic. First thing on a Sunday. Did you guys just wake up? That's awesome. Okay. Now, well, there you go. That probably is what I should have done. So, return-oriented programming. First, who am I? I'm Pandatrax. I like to tear things apart. I don't build things, but they asked me to write the code for the badges, and you got what you paid for, right? Because I don't build things. I also teach an exploit development class, which a lot of people seem to like. So check me out on Twitter. What's that? Oh, thank you, Ray. Yeah, thank you, man. I appreciate it. Yeah, I just taught my intermediate class for the first time, and I think I finished the material like at 4 o'clock in the morning the day before, maybe. Okay. So today we're going to talk about ROP, and the reason why that we want to use something called ROP, which is return-oriented programming, is because we have new exploit mitigations in place on operating systems in our applications, and normally whenever you take or look at any type of exploit writing course, you're starting out and you're writing an exploit where you are executing code on the stack without having to do anything, right? Pretty much you're going to find a jump, ESP or something like that. You put the shell code on the stack, you run your exploit, executes code on the stack, and you're like, yay, I'm done, right? But in the real world these days, that's not really the way things are, right? There's mitigation techniques they're in play that prevent you from doing such things. So, whenever you do that type of an example, you're talking about, the way the world was back in, 50 years ago, or 1988, something like that. So, what is stack prevention or stack execution prevention? It takes advantage of the CPU, and there's a flag in the CPU that tells the CPU that areas of memory are not executable, right? So if you put code there and try to execute it, it's just not going to do anything. It's actually going to segfault the application, and it's going to crash because it can't execute that memory. So when the application sets up its memory, different areas get set this way, non-executable. One of the areas of memory that gets set this way is the stack, right? Because you shouldn't be executing code off the stack. Amen. So there's different ways that, this mitigation technique has been implemented over different OSs. Red Hat has Exec Shield. Other Linuxes have PAX. OpenBSD has, whatever that is. And then Windows has DEP. And everybody's heard of DEP, right? Because that's how Microsoft saved the world. Okay? And we're going to talk about, how we can get around DEP and execute our code anyway. So this is going to be pretty much a demo. So I did not pray to the demo gods this morning, so I am sure that my Windows VM is going to crash or reboot right in the middle of this. This is fine. If you can't read any of that hex, either it's okay because you probably don't care, or you might want to care and move forward because I can't make this any bigger because of the resolution. Okay, so I've got a machine here, and oh yeah, my machine rebooted. So let's see how DEP is set up. I had this all set up beforehand, and of course it had to reboot because I've got like an unlicensed copy of Windows. So here what I've done is I've told Windows I want to turn DEP on for everything except for the application that I'm about to execute, right? Now by default, Windows 7 came with turn on DEP for essential Windows programs and services only, which meant every other application that was running on your machine didn't have DEP turned on. Good job, Microsoft, right? So you actually have to go in this, and which is funny because I don't know if you saw what I just did, but I went into I right-clicked on computer, I got into the system settings, I hit advanced system settings, that kind of makes sense. And then I went to the advanced tab, and then I went to performance settings. I'm not really understanding where we're going, right? Because I'm trying to keep code from executing on the stack. And then I find over here in this tab that's kind of hidden, data execution prevention. And then I have to turn it on. Then I have to reboot my machine. Yeah, go ahead. Emmet's completely different. But I think that Emmet, you can have Emmet turn DEP on the application. Yeah. Yep. Yeah. You want DEP on because you don't want people to send exploits to your application and execute off the stack. And I'll show you that happening in a minute. So for my Pony server, and I think I spelled the name wrong, but whatever, I turned DEP off. Okay, so I checked the box, but I had to reboot my machine to get this to work, right? Good job, Microsoft. And I'm going to, now that's turned on, I'm going to go and start up my service. So I wrote this service. It's got tons of vulnerabilities in it. It's for my class, right? And I'm going to take exploit and send it to the application. And then if I go and look at my machine, my server hasn't crashed yet, but if I go into and connect to the, here, let me, connect to the server, right, and see, and I think it was 4444. Let's do that. I've got a shell, okay? And all I did, so for those that can't see it, this is a Windows shell. I just connected to the port on the box, on port 444, and I opened up a bind shell, right? And the way I did it, if I look at my script, let's stop that. Let's look at the script. All I did was here, I have a jump ESP, right? There's jump ESPs all over your application. I overwrite the saved EIP to then go to the jump ESP, and it jumps back to where my shell code is on the stack and executes it. So DEP is not turned on, and it's a pretty simple script. I mean, that's pretty much it. And I exploit my application. So DEP came out, and they were like, we're gonna make it so that that doesn't happen, right? So let's go in and turn it off and see if it works. Performance settings, oh, yep, data execution prevention. We're going to check these boxes. Okay, now DEP has been turned off from my application. So I'm going to start, it's been turned on, right? So it's going to keep me from executing code off the stack. So if I go and execute that again, get out of that. No, not to, if you change the bullet to make it so that depth's turned on for all of your apps, you don't have to reboot. But once you have it turned on, then you can turn on and off depth for individual applications, right? So now, I'm going to run the non-ROP again, right? And I just lost my window. And I'm going to execute or try. Actually, let's go back to the Windows machine. And we see that crashed, right? So now if I go back to my netcat and try to connect to the listener that I opened up just a minute ago, it shouldn't connect, right? Nothing happens because the bind port didn't like open up. So I pushed the shellcode onto the stack, but then when I used my jump ESP, it jumped onto the stack, and then the code was prevented from executing. So let's look at that in the debugger. So I'm going to start up the app. Connect immunity to it. And I'm going to oh, man, I keep doing that. Sorry. And I'm going to set a breakpoint at my jump ESP. So here's my jump ESP, right? So I'm going to set a breakpoint there, and then start the application back up again. Now when I go and execute my script, we're going to stop and see what happens. So back in the debugger, our application is crashed. We can see that the debugger paused down in the bottom. And we can see in the status bar at the bottom that we hit our breakpoint. And the breakpoint is jump ESP. If we look at the stack over in the bottom, what is it for you guys? Right hand, right? We see that ESP is pointing at a bunch of hex 90s, right? Those are no ops. So it's kind of like a no op slide. If I hit it, it's just going to slide down. And then below the 90s is my shellcode. Before I turn dep on, I would be able to go and just execute those 90s until I hit my shellcode. But if I go and jump right now, right, now you can see the instruction pane where it's changed, and I have my no-ops in the upper left-hand corner for you guys, right? And if dep was turned off, I'd start executing those instructions. But now, whenever I step through it, I get access violations down below. Dep is working, right? See how that is? If I had turned this off, I would just execute those and execute my shell. And that's how I was able to bind to the port previously. But now I can't, right? It's broken. So how do we get around it? Let's go back to what Mike talks about, right? So we observed, for this slide, we observed the access violation. So what is return-oriented programming? It is a way of chaining sets of instructions that are in the application already and to do what you want to do. So in the application, there's sets of instructions which we will call gadgets, right? And they are all followed up by a return, right? When you overwrite EIP, the saved EIP, and make it so like I was going to the jump ESP, what's happening is you're returning out of a function, right? And then that memory address is executed. So I find a jump ESP, whenever the return hits, I go to that instruction and execute the instruction. In ROP, we're kind of doing that type of thing. Yep. Oh, I'll get there. Yep. So whenever I I completely lost my train of thought. Thank you very much. So before I was sitting this morning, I have to say, this morning I'm sipping my coffee, trying to wake up. my head hurts like something fierce. And Jennifer sits down in front of me with her oatmeal, right? And she's like, I'm going to heckle you today, right? So thanks, I appreciate that, because that completely threw me off. Keep going, good. This is fine. Okay, so I'll answer your question because I have no idea what I was talking about. So Turing complete means with gadgets, if you have enough gadgets, and we'll talk about what they are in a minute, you can pretty much write any application, right? If you have enough gadgets to work with, you can pretty much write an application based on all of the gadgets that you find in the application, okay? And the nice thing about using ROP is you're not executing code off the stack. All you're doing is you're pushing instructions onto the stack and then utilizing the behavior of the ret to jump to these sets of instructions to execute what you want. But the sets of instructions are actually in executable space of memory, right? And then at the very end, there's a ret. What a ret does, all it does is it pops a memory address off the stack, and then it jumps to it, right? That's all it does. So if you put a bunch of memory addresses onto the stack that lead to a ret at some point, you're going to hit the ret and then pop off the next memory address off the stack and then jump to that. And I'll have examples in a minute. So what is a gadget? Pretty much kind of went through it. It's like it's all over in your instruction space, and they're just sets of instructions followed by a ret, right? There's other types of gadgets that end in other instructions, but we're going to only talk about the ones that end in rets. So you'll have instruction, 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 and then a ret, okay? Now, the nice thing about x86 is it's a variable length instruction set. So a no-op is 1 byte in size. It's a hex 90. But then an add ESP, like add 90 to ESP, is a longer instruction. It might be 4, 6 bytes long. This allows us to find even more gadgets in the instruction space because of the way you can jump to the memory addresses in the middle of maybe existing instructions, and I'll show you that in a minute. Like I was saying, I was getting ahead of myself. As far as the gadgets, normally a program has all the instructions set up in memory based on a 4-byte boundary, right? But if you jump into the middle of the instruction, then what gets executed might look very different from what the real instructions are. So that adds the number of gadgets that you might end up being able to use in the application that you're targeting. One note, due to popularity of ROP, there's been a lot of research into trying to keep this from happening. I know that there's a couple of universities that have been working very hard to figure out ways to keep people from using ROP to execute shellcode on their in application space. So here's a really good example of gadgets that are hidden within the instructions in an application. So in the top example, I have the original instructions. I have an OR instruction, and it starts with 83, 0D, 0C, yada, 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 right? And then there's a test, EDX, right? Now, if I jumped to where the 0D is, right, and start executing from there, I get a completely different set of instructions here, right? So the OR instruction turns into a different OR instruction. It becomes an OR, EAX, and a number. And then the next instruction after that is an add AL. So if you look at the top, you have 0D, and then this part right here. And then in the hidden gadget down below, that's my first instruction. You see how that is? And then the second instruction is 04, and then this F7 down here, right? And that becomes the add. And then my return becomes this here. the C2, and the bunch of zeros. You see how that is? So I just created new gadgets or instructions by jumping to the address of in the middle of an existing instruction. Any questions about that? Yeah, go ahead. Yep. It's sort of like that. It's more like let's say you have a function, and there's a bunch of instructions inside the function, right? The first thing that a function will do is save EBP, right? So there's a move, push EBP onto the stack, and then you move ESP to EBP. Every function has those instructions. And then the function has the instructions to do whatever it's supposed to do, right? So what I'm talking about is if there is any rets in that, ret opcodes in that function, then what we're doing is we're building backwards from that C2 spot and seeing if there's any valid instructions that we could utilize. Yeah, yes, in this example, yep. Does that make sense? Okay. So what are gadgets, you ask? So a gadget can be anything. Like, let's say I need to pop something off the stack and put it into a register. I can have a pop EAX, a pop EDX, and then a return. It's a pop-pop ret. You probably hear about pop-pop rets when you're doing SEH exploitation, right? In this example, maybe I need to put something into EDX, like a memory address or a number or something. I'll put it under the memory address for this gadget, and then whenever I go and execute it, the next thing that will be on the stack is the value I want to pop into EAX, right? And then I might not care what I put into EDX, and then I'll put some junk in my exploit. And then whenever this gadget executes, it'll pop the value that I want to put into EAX, and it'll do that. And then it'll just pop junk into EDX because I don't care. And then it will return. On my stack, I'll have another memory address for the next gadget. It's going to pop that off into EIP and then execute the next gadget. The next example is a little bit different. Let's say that I need to pop or add 10 to ESP. This is a bad example because normally you don't add something to ESP, but let's pretend that it's like I had just put a negative number into EAX, and I want to make it 7. If I add, or 9. If I add 10 to EAX instead of the ESP in this slide, then that would give me my 9 that I'm looking for. And then I have to deal with these pops, right? I put junk into EBX and ESI after that. And then I get my return. I have my next gadget that I need to execute. It'll get popped off the stack, and I'm off to the races. Does that make sense? Any questions? Cool. So you're probably wondering, Doug, how do you build ROP chains, or how do you find gadgets, right? So there's tools for that, right? Mona is a really good tool for finding gadgets and building ROP chains on the Windows platform. There's a bunch of Python scripts like ROP gadget that you can download from GitHub to build ROP chains and find gadgets on the Linux platform. So what we want to do is we've got all these gadgets that are in our memory space, and we want to start creating chains of different gadgets to do the things that we want to do, right? We have a destination in mind, but we have to get there, right? For example, dep's turned on in this case, right? I want to turn dep off, right? I want to execute stuff on the stack. Why don't we just turn dep off for the memory space that we put the shellcode in, right? That would be cool, right? So I'm going to build a ROP chain to go and turn off dep. Great job, mitigation techniques, right? Okay. Another thing that we have to deal with is ASLR. ASLR is the randomization of memory space, right? The stack is normally under ASLR control, so things are always changing. The memory addresses are always changing on the stack. We want to make sure that that's not happening with our gadgets, right? Because when I write my exploit, if the memory address for my first gadget's 1, 2, 3, 4, 5, 6, 7, 8, right? And the next time I start up the application, ASLR is under control, is in play. It randomizes the memory addresses. Then it's 987654321. I'm kind of screwed because then I can't execute my gadget. And you have to have control over ESP, right? Because ESP is where we're putting these gadgets on the stack, and we have to be able to point ESP to our gadgets, our chain, to be able to do the rets, right? Because a ret is just popping that value off the stack for us. So here's an example. I need to put 2C into EAX, and hex 00 is a bad character, right? So I can't just put 0000002C into my exploit, because the first 4, 6 zeros are going to just break my exploit, right? Because hex 00 is a bad character. So what I do is I build a chain. First thing I'm going to do is I'm going to find a pop EAX, right? That's at the top of the chain. And I'm going to pop a value into the EAX register. I'm going to choose FF. Anybody know what value that is in decimal? -1. Yep, it's -1. I didn't have to use any zeros to put that into the register. As soon as I execute that pop, it's going to take that value of F's, put it into EAX, and now have -1 in EAX. So how do you think I might get to 2C? I just find an add, right? A gadget that has an add EAX. And then I just start executing them until I get to that value, 2C. And then it's followed up by a ret, because all gadgets are followed up by a ret, or something that's similar, right? Some type of jump, whatever. Do you see what's going on? So now I have 2C in EAX, and I didn't have to use my bad character, which was the hex 00, which would have broke my gadget. So now I have a chain of gadgets that did what I needed it to do. Make sense? Cool. Yeah, we can do it again. Let's just rewind. Wait, who's awake right now? Because I think that Bill was falling asleep. Oh, good. There's a couple hands. Good. I'm glad. That's good. I'm not sure if I'm awake, so that's good. Okay, so I said that Mona would be a good tool to find gadgets on the Windows platform, right? So I'm just going to go and say, hey, Mona, ROP for me, right? And she's going to go out and find gadgets. She's also going to go out and build, try to build chains for me. She would tell me about interesting gadgets that I might be, might be able to use. She'll get all of them that she can find, right, in the application. And she'll put them in files for me. So like ROP.txt will have all the ROPs that she found, right? Very cool. If you go and do this, and you have a big application like, let's say, Wireshark, right? And you say just Mona ROP, right? Sometimes Mona doesn't look and see which libraries it might need to use, and it will go and try to find ROPs for, gadgets for all of the libraries that are being loaded into Wireshark. And when that happens, your VM's going to lock up really hard, and your machine's going to lock up really hard, and you're going to be like, I need coffee, and I won't be able to use my machine for hours, right? So if you do that, just be aware of what you're doing and just tell Mona, I'm interested in looking for gadgets in these DLLs, and just zero it down. But unless you want your machine to get real hot and not be able to use it for a long time, okay? But, I've done it plenty of times, yeah. It's aggravating. That's why I'm warning you. Okay, so You might be thinking, okay, Doug, you just said, let's turn ROP off, right? Well, on Windows, there is a bunch of functions, but we're going to pick on Virtual Protect right now. That will be able to help us turn DEP off in a specific area of memory. Virtual Protect modifies the permissions of memory, right? And Mona is really nice because she will try to create a chain utilizing Virtual Protect. So she does the work for you. Sometimes she might not be able to find the correct gadgets that she needs to be able to turn DEP off in that area. So you're going to have to go and fix the chain. But she does a really good job of setting things up for you. So here you can kind of see an example of this. Down below, I kind of took a snippet out of the beginning of a chain. And you can see how the very first thing that she does is she finds a pointer to Virtual Protect in the application itself, right? And then what she does is she figures out a way so that you can pivot on the pointer and then call Virtual Protect directly from the kernel to disable DEP. Virtual Protect is so cool because you can go, I've got this area of memory like the stack, and right now it's only read-write. And I want to be able to execute off the stack. Virtual Protect, can you take these 100 bytes and just make it executable for me? Sure, we'll do that. That's cool. We can do that, right? Thanks, Microsoft. So here's a bunch of different functions that we could use. Let's say Virtual Protect isn't available in the application, but Virtual Alloc is. There's different ways to do it, but we're going to pick on Virtual Protect right now. Normally, Virtual Protect is very reliable, right? We're talking about Windows here. If you're looking at Linux, if you like to pick on Linux, mprotect is a good thing to do. That's a function you want to do man on. Okay. So Virtual Protect is a kernel function. I have to say, WinXP was awesome. I loved WinXP because everything was static. There was no ASLR turned on a lot of the OS libraries, right? Including the kernel, right? So you could just say, call Virtual Protect directly from the kernel because there's no ASLR. There's no randomization there. You could always reliably use that function. Well, Windows 7 came along. They got a little smarter. And now, ASLR is turned on those OS DLLs. So all we do is we look for the pointer that is being used within our application to point to it because it's always going to be dynamically created every time that application runs. And then we can just pivot off that pointer. Good job, ASLR. Right? Thank you for protecting me. Awesome. Yeah. So here we are. We have the layout of how to call Virtual Protect in a function. The Virtual Protect function. So on the stack, I need to have the address of Virtual Protect at the top, right? Because I'm going to call it. I'm going to return to it. Remember, we need to return to our gadgets and stuff. We're going to do the same thing with Virtual Protect. So the first thing that's going to happen is we're going to return to that, the memory address of that Virtual Protect. Then the next thing that's on the stack is going to be the address that we go to after the function is done, right? We're kind of taking advantage of how functions are called, especially on the x86 architecture here, right? Because whenever functions really get called and you're not messing around with it with exploit, the last thing that gets pushed onto the stack when we call a function is the address that we're going to return to, right? So in this case, we're going to put the address of the shellcode that we want to jump to after Virtual Protect turns off turns on execution for that area of memory. Then we're going to tell it how many bytes we want to change the permissions for. So we might, how big is our shellcode? 100 bytes maybe on a Linux exploit, maybe like 500 100 to 700 bytes for Windows shellcode, right? We're going to have to tell Virtual Protect we want this much space that has the executable bit turned on, let's say. Okay? And then we want to tell it, what the new permissions are, right? So hex 40 on Windows is, the value you want. You just have to remember that, or take a picture of this slide, whatever. On Linux, it's going to be pretty easy. Everybody knows about chmod, right? How do you make something executable in Linux? You say chmod 7, whatever, right? It's the same thing. We need to tell mprotect on Linux to change the permission set to 7, right? So we get read, write, execute. And then it's something really weird about Virtual Protect, and I am not a developer. I said that at the beginning, is that you have to take the permissions of the page that you're making the change to, and then apply the current permissions to some other area of memory. So you just choose something randomly that's in the address space of the application and just say, do it to that. And I don't really know why Virtual Protect has that in its parameters, but you just have to deal with it. So you just choose something randomly and it goes and makes it read-write. I don't know. Okay, so let's test this out. Let's check it out. Let's go back to demo and hope that my Windows machine just didn't reboot on me. Oh, good, it's back. Okay, that's always good. And what we're going to do is instead of using my regular exploit where I was using the jump ESP, I'm going to now utilize a chain that Mona created. So first thing I'm going to do is I'm going to fire up my application, fire up immunity. I'm going to attach to the running process. I'm going to start it up, stop it. And then I'm going to say, Mona, right? Mona, please find ROP for me, right? And, oh, wait, while you're doing it, I want to make sure that, let's see, dash, yep. Make sure that you don't find any addresses with hex 00 in it. This is small, I'm sorry, but I'm telling Mona to ignore any memory addresses with a hex 00, okay? Because hex 00 will break my exploit. Remember in my example I said that? This application has a problem with hex 00. So she's going to go off, she's going to go find it. And she didn't hang my machine, right? Because this is a really small application. I wrote it, and I'm not a developer, so it's even smaller. Okay? And if I go into where Mona's writing her logs, I can go and look, and sure enough, here's my ROP file, right? If you can see that, small. Here's my ROP chains. And then she gives me ROP suggestions. That's pretty cool. So if I don't want to dig through every single gadget, I can at least look at the suggestions to see what she thinks is good or not, right? But let's look at the chains, see what's in there. So if I scroll down a little bit, you will see that the first thing that she does is try to make a chain for Virtual Protect. Let me just move that over so you can see it. And what she's going to do is she's going to use a method of that utilizes push-AD. Anybody know what push-AD does on an Intel processor? It takes the registers and pushes them onto the stack. So all that Mona needs to do is put all the values that she needs to call Virtual Protect and put them in the right registers. And then when push-AD is called, it's going to take all that stuff and push it onto the stack. And then she's going to turn around and call, the function, just like we just talked about. The way it will be set up exactly the way we were just, talking about. And then if you scroll down a little bit, and I'm going to have to move this over again because my window's too big. She gives an example in Ruby, the example in C, and my favorite, the example in Python, right? So I can take this gadget, or chain of gadgets, and copy them into my script and utilize that. So let's look at my script. If I scroll down, here's my chain, the same chain that we just saw. Sorry for those in the back. Trust me, there's stuff here. Because somebody said highlight it. I was like, yeah, I can highlight it. Here you go. Can you see it better? Yeah, that's good. This is fine. Okay, so this is the chain that she made for me. I was really lucky, well, kind of, that she was able to create a chain to do everything she needed. Some applications, like this application before I started like developing it, had a lot of parts of the chain that she couldn't figure out. So what did I do? I went and started creating these gadgets. I was like, okay, I need a pop EBP. I'll just create one, put it into the code, and then recompile it. And then all of a sudden it was there, and Mona was like, hey, I just built a chain for you. That's awesome. Okay. But then down below, instead of my jump ESP, remember here, I'm going to put my chain in there instead, right? So I'm replacing the jump ESP, because I can't jump back to the stack, it's not executable. And I'm putting my chain there of gadgets. But my entire script, the rest of it is exactly the same. The shell code is afterwards. The script is the same, except for the fact that I'm using ROP to turn off dep in that area instead of just jumping to the shell code itself. Really, really cool, right? Nice. Okay, cool. So let's see what happens in the debugger to see exactly how the chain is working. So I'm going to I'm going to be able to try to figure out how to use Vim. Now that I do, I'm going to start this back up. I'm going to take the first memory address. Actually, let's look at this real quick. The first memory address of the chain is, I know you guys can read it back there. Can somebody read it? It's 6, whatever, I don't care. I'm just going to copy it, whatever. And I'm going to set a breakpoint in the debugger. So, here we go. So the first thing that happens is I want to pop EAX. So that's the first gadget in the chain. So I'm going to set a breakpoint there. And the instruction just turned light blue, right? So I know that there's a breakpoint there. And I'm going to go back to I'm going to fire up the application again, F9. And now I'm going to send my exploit. So ROP. Okay, I just sent my exploit. Okay, if I go back and look in my debugger, sure enough, down in the bottom, I know you can see it, it says it hit a breakpoint. It's the number, the address that I set. So it's that pop EAX. So if we look at the stack over on the left-hand side, we see, I don't know if you can see it, I'll make this a little bit bigger, that there's the pointer to virtual protect on the top of the stack. I put that there. Well, wait, I didn't put that there. Mona put that there, right? I didn't put that there, but I put it in my script. So now if you look, if you compare the stack from that point down, all of the values that are on the stack are the stacks that are in my chain, right? Now we're going to start executing these gadgets based on my chain. Do we know how we got here? Anybody know? Just so that we cover that? Yeah, go ahead. Yep. Other stuff. Yeah. Perfect. Yeah. Exactly. The other thing to know is I overwrote, so I have a function that has a vulnerability in it, right? This one has a stack buffer overflow vulnerability in it. Some string copy doesn't have bounds on it, right? And I can overflow the buffer. Every function, when it's done, it returns back, like we said, to a specific, to the calling function, right? It needs to know how to get back there. That ret, I overwrote, I overwrote the saved EIP, and that ret is executing my first gadget. That's how I got here, just so that I'm clear about that. So now I'm about to execute my first gadget. So I need to take the memory address of the pointer to virtual protect and put it in EAX. So if I step through, look at EAX, it just changed. It's now got the virtual protect address in EAX, right? The next thing that Mona is going to do is it's going to do some trickery to switch it so that it's not the pointer anymore, but it's the actual memory address of virtual protect in the kernel, okay? So we're going to just step through that quick. Oh, I just executed the return. If you noticed, at the top of the stack, the memory address for the pointer of virtual protect is gone because it's been popped off, right? And we've gone and returned to a different gadget. So now we have a gadget that has a move instruction in it. And this is the trickery that's going on. But I'm now in a place where there's a new gadget being executed. So I execute the first instruction, which is the move. And then here I'm at the return. It's going to pop that memory address that I have on the stack next off and jump to it. So it's some other gadget that we're going to jump to, right? So now we have a pop ret, right? She wants to pop the next values off the stack and put them in the different registers. Sometimes you have to deal with gadgets that have junk instructions in it. So more than likely, she needs to push, do the push. This might be a bad example, but she needs to, let's get back to that because this is actually these are all good instructions. What she's doing here is she's going to push EAX onto the stack, which is that pointer, and then she's going to pop it into ESI because that's where she really needs it, right? So when we push it onto the stack, it's going to push my chain down, right? So now that value is now back onto the stack, and then what she's going to do is pop it into ESI, right? It didn't affect my chain at all. In my class, I tried to do this example, right? And I think I might throw my back out if I try to do it here. But I said, pretend that you have painted lines on the road, right? And those are that's your chain, right? And every time you want to execute a new gadget, you just freshly painted, right? So every time you jump on a new line, you're going to get like footprints in your new line, right? And pretend that every time you execute a new gadget, you kind of jump this way. I'm going to go right through this stage. And put your foot on the next line, right? But then if you need to move things around with push pops, it's kind of like jumping backwards, right? You're not, every time that you jump on a new line, you're kind of utilizing the next gadget in the chain. But if you're doing something like this where you're pushing and popping, you're kind of jumping backwards onto lines that you've already jumped on. And I would love to do that right now, but I'm really scared that I'd go right through the floor here. And then whenever you're ready to start executing new gadgets, you have to make sure that on the stack, you're back to the next gadget that you want to execute on the stack, right? So if you do a couple pops, or I mean a couple pushes, right? You're pushing data onto the stack, like this one is doing one. You have to have the same number of pops to get back to where you were to get to the next gadget. Does that make sense? I would love to jump back and forth, but oh yeah, I can jump down there after, okay? So then we have a bunch of other things that she's doing this trickery to be able to, figure out, where virtual protect is. And I just went past the gadget, but if you look in EAX right now, the value has changed for virtual protect to the kernel, right? She did her trickery. Now she's in the mode of trying to set a specific number, probably, the permissions. I think hex 40 was permissions, right? She's going to go, I think that she just pushed a value into EBX, what is it? FF, DFF, right? And now we're going to negate that. Kind of like what I did before. I had -1, which is FFFFFFF, and then I added to it, right, to get a number that had nulls in it. She's doing the same type of thing, But she has a neg instruction to be able to just do 2's complement to that value to get the positive number without putting hex 00 into the exploit. Make sense? And if you look at EBX right now, and then execute that instruction, we now have 201. So 201 is the size of our shellcode, must be, right? It's hex 201, not 201. Just be aware of that. Okay? So now if I just keep on stepping through, you can see that she's putting different things into each register, right? And, oh, here's our push AD. So now if we look at the registers, and we go back to that slide that I had before, right? They should line up. We have in EDX hex 40, right? We have in EBX hex 201. The 40 is the permissions. The 201 is the size of the page that's going to be, changed. Make sense? She's doing this using gadgets. She has not executed anything off the stack yet. Now we're about to execute virtual protect. So the next thing that we're going to do is we're going to use push AD, push all those values onto the stack. Let's do that now. Now if you look at the stack down in the lower right-hand corner, you can kind of see in through here, right? There's our virtual protect. This is the memory address that we want to jump back to. Here's our value of the size of the area that we're going to change. And this is the permission right here. Make sense? That's pretty cool, right? Yeah. Thanks, Mona. I mean, you can build these chains yourself, and it's great exercise, right? Do you like the Rubik's Cube? This is just like the Rubik's Cube, right? Or maybe worse, or I don't know. I am horrible at the Rubik's Cube. But my son can do it in a minute. And I'm like, what just happened? And he's like, I did it. And I'm like, yeah, but how? Like, I don't even know how you can look at it and like know what's going on. I don't know. So maybe it's a little bit harder than the Rubik's Cube for some people. Okay, so then what I need to do now is Mona is going to set it up now, so now we are ready to call virtual protect. And you can kind of see it on the stack. Immunity is kind of trying to figure out, oh, we have a function that's about to be called, right? And you can see how it says call to virtual protect. And then the address equals, Immunity knows what the virtual protect parameters are. And she's like helping me out. She's like, oh yeah, look at this. Immunity is like, yeah, you're going to call virtual protect, and these are all the parameters for that. Good job. And I can look, and I'm like, oh yeah, look at that. The address and the size, the new protection, execute, read, write. Yeah, that's cool. And the old protect, which I don't understand, right? Next thing I do is I'm going to call it. There's a bunch of little things that happened. I'm kind of stepping through like virtual protect and some other things, right? But let's get to the point where, there's the actual call to virtual protect, right? And now, whenever we return, we have a jump ESP. This is a memory address that Mona found, and she put into her chain. And we're back to the beginning. This is back where we started, right? Before we started talking about ROP. We were ready to jump to ESP and execute code, the shell code. If you look on the stack, there's a bunch of hex 90s, right? Hex 90 is a no-op. So you have a little bit of a no-op slide, whatever, right? And we're going to see, remember what happened here when we had dep turned on. At this point, we got an access violation, right? Let's see what happens. Oh, no ops in the execution stream, right? Let's see if we get the access violation. Nope. I'm executing no ops right now. Oh yeah, that's excellent, right? I'm getting really excited now. Really, oh, there's my shellcode. Boom. Okay? Did you see what happened? We just turned off dep. That mitigation is no longer in play, right? So let's see this in reality. Like, let's Let's see if it really works. This is where I should have like prayed to the demo gods, right? And said, please work, just do it, please. And I'm guessing that when I'm about to do this, Microsoft is going to give me the finger and say, and like reboot Windows on me or something like that. I don't know. But let's see if it works. Oh, and let's make sure I wasn't messing with you and had virtual. Yep, I have it turned off. Good. Or I mean turned on. So DEP is turned on. Good. I just want to make sure. Okay, so now I'm going to execute this. ROP. Right? Did anything happen? I don't know. If I look at the running process, it's still running. So I didn't crash it. Remember before when I did this, it crashed the process. The only thing I did was I turned DEP on, and it crashed my process. But now, it didn't. So let's go back and just double check and see what's going on here. I have my netcat to port 4444. Connect to it. Boom, here's our show. Okay? Thank you very much. So I'll go back to my slides and go way to the end. Any questions? Yeah, go ahead. No. So I turned DEP, right now on my machine, DEP is on for all running processes. So that will not, there's nothing else. I mean, oh, if you turn it off? Yeah, so I think that's a good question. If you turn DEP off, yeah. Oh, yeah, I'd love it. Right, I wouldn't have my show anymore. But if you have DEP turned off, I've had certain situations where the exploit won't work because Virtual Protect is like, I think it might throw an error and say, I can't do this because it's already executable, right? Or something like that. So sometimes your target might be vulnerable anyway, and then when you go to use ROP, it might not work because you're trying to turn something off that's already off. So maybe. You have to play around with it. But then you can just go back to my first script, right, and just execute that. Done. Bang. Yeah. Any other questions? Yeah, I guess she does. Good question. I like that. Nice. So that's my talk. Hope you liked it. Hope it woke you up. Thank you.